Swayam Prabha. Digital India. Educated India.
All right, so now you know how GAs work, a little bit, the GA operators, how to handle constraints, a little bit of understanding of how GAs work. So this slide onwards I have added lately, like few years now, because giving a talk like this or even 1 hour talk, there will be some people, smart people sitting and asking me questions. How big a problem have you tried? Because all along they're sitting with this recombination, selection, they think it's like a child's play. It's like some game I'm playing. It's not serious stuff. A lot of randomness in them, right? So I thought I need to find a big problem to shut them off, okay? Fortunately, I found one when I was in IIT Kanpur. There's this company from Lucknow called PTC Industries. It's a foundry, basically, only surgical foundry. So surgical equipments, all these they made. But it's so popular, I think it's the best in the country, and also probably come very close to best in the Asia. They get lots of order. I visited their plant, huge, very sophisticated foundry processes. They have written an Excel code. So I used to, when I was in Kanpur, Sarvana may have attended one of those or know about it, that I used to offer every year a short course, like 5-day course like this. And that I used to keep open for anybody, student, faculty, industry. I would get 80 to 100 people, sometimes maybe 50 to 80 people coming, because that time it was new, ideas were new, they wanted to know. So when one of those, that person, the R&D chief of that company also came to know and came, and he said, Professor, I need to have some time with you because we have a problem that maybe your methods can solve. So in one of the afternoons, I sat with them and they showed me an Excel code. So what the problem is that you melt some metal. This is not from their company. They have lots of restriction they put on me. After I solved it, I think it was probably early 2004 or 5, I did it. And they put on me a 10-year restriction that I cannot talk about it. Okay. So after that is over, then I did all the extended work I'm going to show you. They melt some metal, and I know exactly how much. It's 650 kilos. It's a big vessel of metal they will going to melt. And now they have to make lots of castings. And they have like 2 months, 3 months of order now. And this guy, chief, goes around, gets more orders and all that, so he's hardly there. So he says he wants to schedule it for at least a month or 2. Okay, and give the whole schedule to the foundry people, and they will just do it accordingly. So he needed a code that's going to do it. So he wrote an Excel code where all of these are fed, weight of every castings that they have to make, and then the vessel size, and then how many per day they can do this. It's about 13 times they can do per day, because it takes about 2-3 hours to melt and everything. It's more complicated. They have 2 different size of vessels, but when we gave the code, we had all these details worked into it. But here I'm showing you with 1 vessel. Okay, so all these parameters are known beforehand, and now you melt 650, you are going to pour it to fuel, and then let's say you've utilized 630 kilos. 20 kilos are still there, you could pour, but none of them is less than 20 kilos. I'm giving an example here. What you're going to do is going to be a waste, right? And then you melt some more, come back after 3 hours and pour again. Then you think, oh, what if I could have done with 640? Then maybe 10 kilos would have been a waste. So if you do it 1 or 2 times, you could do manually. But if you have to do 13 times a day for 2 months, it's a lot of order to do manually, a lot of scheduling. So you need to use an algorithm like this. So they set it up on an Excel sheet and they run it after dinner, and next day morning they will get some results. And they would get about 70 to 75% utilization. So 25 to 30% of the 650 will be wasted. They could manually fix it also, they said. So it's not something that they're proud of, but that's all they were doing. Okay. He said, if you can give me something 90% or more, we would be happy. Okay. So I took that as a challenge and I said, let me see what I could do. So I calculated how many variables do I have if I go for 2 months of projects, 2 months of scheduling. It's about 50,000 to about 100,000 is what you get. So it's, in any standard, it's a very large problem. What's the problem? Here is the objective function where xij are your variables. It says from the ith heat, ith time you heat 650 kilo, jth casting, how many copies you're going to make, because every casting maybe you have 10 copies to be made, 8 copies to be made, like that. And this is the total metal utilization which you want to maximize. This constraint says, so let me give you an example. This is an X matrix because xij is a matrix, right? So this is the first hit. It says from the first hit, you make 1 copy of the second one, 1 copy of the third one, 2 copy of the 7th one, 1 copy of the 8th one, and you will be utilizing 623 kilos out of 650 of melted. So the utilization is 95.85%. Next one, you do this, you have utilized 94.62%. Like that, if you do 10 times, you may have met these small orders. First one, you have to make 7 copies, second one, you have to make 7 copies, like that. And you are meeting them. So average of that is you want to maximize, this is this actually. And this constraint for one particular I is that this has to be less than equal to 650 because you cannot utilize 651 kilo because you haven't melted 651, you only melted 650. The numerical methods doesn't know that, so you have to put that as a constraint. This is the resource constraint which says whatever you are utilizing should be less than whatever you have melted. Make sense? Then this constraint says the order sum up has to be 7, has to be the given R. It's an equality constraint. Okay, so now if you look at this, this is a linear function of x. Objective function is linear to x. This constraint, there are many, but they are linear in x. Look at that, linear in x. There is no x square. This one also linear in x. So everything is linear. What do we call it? Linear programming. And I told you with linear programming, we can go to millions of variables. So what's the problem here? We only need 50,000 to 100,000. The problem is this. Every x, which are these numbers, can it be non-integer? If this is 1.5, what does it mean? I'm going to make 1 copy of the second one with the 650 and then 50% of the another one. Is it allowed? No, either you completely do it or not do it. So 0 or an integer is allowed. This itself makes all the linear programming stuff very difficult. I showed you the only way they do it is branch and bound. And I also mentioned to you yesterday that this is an exponential method. That means if you have few hundred variables, it's probably okay. But if you go to thousands, they don't work anymore, right? That's the problem. So what we do is, as always we do, first we try a standard existing code. So we actually tried Cplex, and another method we tried with Octave, which is like parallel to, it's a free version of MATLAB called Octave. GLPK, they have one to do the integer linear program. Later on, we also tried Gurobi optimizer. So I talked about this, it's an exponential method called branch and bound. Let me show you some results. So I first took a very small version of the problem. I adjusted the weights and all that, number of copies in a way that I need about 300 variables. Small size problem, not 50,000. Okay. So when I run Cplex, let's forget the GLPK. When I run Cplex, that's 310 variable, it takes me 0.05 seconds. Okay? And no standard deviation when I run it many times, and I get 99.256%. This is the known optima. I mean, I could prove this is the optima. Only 0.05 seconds, Cplex. Excellent, right? Then I increase to 1000 variable, I increase all these data. Now it takes 0.13 seconds, which is also very small, very quickly it does with the optimum. Then I go to 2000, it cannot solve. Okay? So you see, small numbers, excellent. You can use it, but anything larger, it cannot. So then I was wondering, when does it work? When does it stop working? And I found that around 1800, it does work. It takes 1.22 seconds, but it works. 1900 doesn't work. 2000 doesn't work. So I took a 2000 variable problem. and I want to understand why it doesn't work. So what I did, I took 2000 variable, we ran it with time. So this is in seconds. We ran it for half an hour. Okay, and there are two things it prints out, among other things. One, the blue is how many nodes it has opened, how many branches it has made, because you remember it assumes it's real, and then all the variables that are not integer, it has to branch, right? So how many such nodes it has opened. It turns out when I am at 30-minute range, it has opened about 35 million nodes. 35 million nodes it has opened so far. Of them, this side is how many left, how many are still to be fathomed. Unless you fathom everything, you don't have a solution. I mean, you don't have the final solution. You see, they are fluctuating because sometimes they can fathom more, sometimes less, but still about 35,000, 34,000 or so, still open. So I thought, oh, we terminated a little early. Maybe we should go another half an hour, we should. So we end up running for 15 hours. Both are increasing, which means it's a problem that dimensionality is beating the algorithm. This algorithm is not able to handle the dimension, no matter how long you run it. Okay, so this is only 2000 and we have to go to 50,000. So I thought, no, these are too structured methods. I cannot even change them. So if I have to give them a solution, I have to think fresh. Okay, so we thought of generating or creating a population-based integer linear program. It's a very simple code. We customize everything. We customize our initialization. You see, look at one of these constraints, this constraint. Sum of few numbers. Let me take an example. Let's forget the two dimension. Let me say this equal to 5. One of the constraints is like that, right? If I want to create an initial population that will satisfy these constraints, how can I do? All the x's can go between 0 to, let's say, I take a maximum number. Let's say I divide this by 5. Maybe that's a good idea. I divide this by 5 and make it equal to 1. It's the same constraint, right? So then let me say that because none of them can be 5 because their sum has to be 5. Let's say each x goes between 0 to 1. Each x goes between 0 to 1. And now I'm looking for a few fractions that will add up to 1. How can I create an initial population member that will satisfy this constraint? Any idea that you may have? So I'm actually trying to have 3 numbers which are all fractions that should add up to exactly 1. How can I achieve it? This is how you have to think when you are doing customization. Any ideas come to your mind? Okay, you can think about it later, but let me give you my idea. Let's say each of them I randomly create a number. Let's say this one is y1, which is between 0 and 1. Take a number. Let's say this is 0.4. Next one I created, let's say 0.6. Next one I created, let's say 0.2. Okay, randomly between 0 and 1, 0 and 1, 0 and 1. Is there sum happens to be 1? No, because they are randomly created. But let's see, what's the sum? 1.2. Then, where did I go? Then each of these number I divide by 1.2. Okay, and I call my x1 is this, x2 is this, x3 is this. What if I add them now? What is it going to be? Always 1. Isn't this a nice trick? And I could do this because I am using a very flexible algorithm. I could do anything. I can create my initial population any way I feel like, right? So I create every initial population member satisfies all of these constraints. If you do this little trick, which doesn't take much time to think, you are already starting with a good population. Okay? Now, fixing this doesn't mean this gets satisfied. So we have a mutation operator or called repair operator, which I applied on top of this to try to fix this. So that's my initialization. So it's not a totally random population. It's satisfying at least some part of the constraints. And then mutation to it I'm going to describe to fix the inequality if possible. Then we assign a fitness, and there is a way, I'm not going into the detail, but there is a problem specific way you can fix R here. So we fix the fitness function, then we do the standard tournament selection. I'm going to show you my custom recombination, custom mutation 1 and custom mutation 2, and if terminated, we stop. All right. So this is the one I was, it went up, no? Fixing? Okay. Okay, fine. I already talked about the custom initialization. Let's talk about the custom recombination. So let's say I take a part of my string here, only 4 heats. Okay, this is parent 1 and this is parent 2, right? So how do I create a child? So I look at the first heat arrangements, and it has taken 343 kilos out of 650. On my second parent, the same first heat, it takes 625. Which is better? Second one, because it's close to 650. I have utilized more material. So I take a copy and put it here. Now let's go to the second, which is better? 808, 667, which is better? Both are infeasible, but this one is little closer to being feasible, so that sense it is better. So I take a copy of that and put it here. Third, which is better? 629 versus 606, this is better. Take a copy of the third and put it here. Like that, I keep filling up my child. So that's a perfect recombination. Some things come from first parent, something comes from the second parent. Because in this problem I could do partial evaluation of solutions, I could do that. Now in another problem you give me where these partial evaluations are not possible, I have to think of some other way. Okay? So this is how I do it. Let's say these are my orders, these are the equality constants, some has to be 3, some has to be 2. Now I screwed that up here because I took something from here, something from there, the sum need not be what I wanted. So that's where I use mutation number 1. It's more like a repair operator, I call it repair 1. I try to fix this. This one has to be 2. How can I make this 2? One of the 1 has to go away. So which one do you recommend I should take away? Because this one is already overboard. So I need to start to reduce things from here. And I see, there is a scope. I could take that away. So I took that away. And that makes these 2 satisfied. It reduced, it came close to 650, but still I need to reduce some more. And this is how I fix all others. So this fixing, I could always do with some complexity. It's not big complexity. Then after I've done all that, I fix all of them, then I look at, is there anything that I still can fix here? The inequality constraints, I find that, this one, how can I fix this one? Because this sum I cannot change, right? How can I reorient things so that this reduces? Which still means something I have to take from here and put it to the other. So for example, I could take this one and put it over here, make it 2. It's going to take something away and put it to this one, but maybe it's better to put it on that one because this one is really far away from 650. So this is how I can think and try to adjust. This one I do one pass, and I'm not guaranteeing every time I'm going to fix like this in this case, but the mutation I will always fix. Okay, so I do just one pass, and in case something is left, I use that as a penalty. So that's a very simple idea. Otherwise, I don't know how long I have to do this repeating process. This is more like a game we used to play when you were a child, filling up with numbers, a matrix, so that sum of this side equal to something, sum of this side equal to something, and you can adjust. It's the same game we played here in a computer. Okay, so that's the algorithm. Let's go back to these problems. 310, we got the same accuracy, same optimal solution, with slightly less time, but I'm not bragging about it. 1000 variable, same accuracy, much less time. 2000 variable, good accuracy. This is actually, all of this small size we can prove this is optima. We could in 0.19 second, which was not possible to be solved by Cplex. These are small size problems. Now I take take you 50,000, and I could use this method to take only 10 seconds, less than 10 seconds to give me a solution. 100K, about 20 seconds. Like that, we can go all the way up to billion. So they are okay until here, which means in 20 seconds, maybe 30 seconds, they have a result. Not overnight, not 70 to 75%. So these ones we stop when we get 99.7%. So they are happy with 90%, but when we wrote the paper, we shoot it up to 99.7% metal utilization. So the optima can be somewhere from 99.7 to 100%, but we are sacrificing that to get this kind of performance. So each of them has this kind of accuracy. You see, this is in log scale, the y-axis. The x-axis also in log scale. So if you have log scale, if you have a straight line, what does it mean? It's a polynomial time algorithm. And the polynomial equation is here. See, n is the number of variables to the power something less than 2, slightly greater than 1. So it's in between linear and quadratic complexity. They are all almost falling on a straight line. Okay? So it's a polynomial time algorithm to get 99.7%. Now I'm not claiming each one of them to be an optimum, but it's very, very close to being optimum, right? 99.7% to 100%, somewhere in between. This problem is also known as knapsack problem or multi-knapsack problem, and it's NP hard. So you cannot get a polynomial time algorithm to get to the optima. But from this time to get to the optima will take you that exponential time. So if you don't need to be the optima, you can sacrifice 0.3% of metal, which is about 2 kilos. If you sacrifice, then I can give you a very fast algorithm. To show that it's a very difficult problem, next what I do is I change my target. 99.7 I showed you already. Then I do 99.9, here 99 and all that, and I look at the time taken. You see, this is in log scale, this is in normal scale, and I already get an exponential. So in actual scale, this is super exponential. Okay? So in order to get close to the optima, this is 100%, right? So I'm giving you already 99.9. Optima is in between the two. So if you can sacrifice this much, you can have a polynomial time, very fast algorithm. So many people, when they say, have you guaranteed optima? You use this method, are you saying these are optima? I said, do you really care? If you get to this kind of close value and we are okay with it, then of course, you don't need the optima. So you have to remember that. Don't unnecessarily claim something that's going to cost you a lot of time. Okay? So this is again an engineering approach, right? So in these kinds of problems, I think evolutionary methods are great. And some aspects of problem complexity that can be negotiated with these kinds of algorithm. Let's look at the next big important thing is real parameter GA. So far we concentrated on binary strings and showed you some reasoning. But many problem in practice like the one before, you have only real numbers or maybe integers and things like that. You are not dealing with binary strings. So you have taken completely out the binary string part and you don't have to think in the binary string at all. You just do with these variables. So this is something again, when I joined IIT Kanpur, I used to go to different industries to talk about these methods, optimize and all that. And there will be a bunch of engineers sitting like you. And I start talking about binary coded GA, that every variable you have to code in binary strings. Some people got uneasy, they walk out for some water or something. They are not paying attention after that. And these are the kind of hints you have to take when you are kind of building your career, what people like, what people don't like. So that was kind of stuck in my mind that I have to get rid of the binary string. Otherwise, I'm not getting through the people, right? Again, you have to remember John Holland and all his students that did, except Goldberg, who was my supervisor, they were not engineers. So they were perfectly happy with binary strings. But we took the idea and said we need to apply this in practice. That's where these issues come in. So it's our responsibility to make sure that we develop methods that will work. So what is the problem with real strings or real numbers? You will have a fitness, you will have a function. That's not a problem. So tournament selection is not a problem. You are dealing with function. You don't have to change anything. But the recombination and mutation are the ones that hampers, because there you had a binary string, you put 1 or 2 point cross site and you do this swapping business. Here what you do, because these are some real numbers. So there are two ways you could do. One is you look at them variable wise. So you have two numbers, let's say this is 2.56 and this one is 3.89. come up with two other numbers, maybe 1.25 and 3.12 or something, two numbers that are children coming out of these two parent numbers. It's a little odd to think about, but we call them blending. So you basically took two numbers, two real numbers, blend them to get two other numbers. That means I'm thinking of some kind of a probability distributions around this to create two other number. That's one way. This is called variable wise. You can also look this as a vector. In the n dimensional space, first point will be a point p1, and the second one will be another point, let's say p2. So there are two numbers in that n dimensional space. You need to now blend these two numbers in that vector space to come up with two new numbers. How you do it? It's your prerogative, and that will be your algorithm, right? So I will show you a couple of ways people have done. Let me leave that. Blend crossover was suggested in 91, and then we suggested in 95 the SPX, which has become now default. And there was another one similar to ours proposed almost at the same time called fuzzy recombination. Okay, let me first start with the blend. So we are doing, these are variable wise, right? So we take ith variable, one from first parent, one number, second number from second parent. Okay, so let's say on my real line, this is where the parent 1 is and parent 2 is. What they do is they take the difference, okay, p2 minus p1, and they go alpha times on left of p1 and alpha times of left of p2. Alpha is a parameter. Doing a lot of experiments, they suggested alpha should be 0.5. So you basically go 50% of these on this side, 50% on the other side, and create a random number here, anywhere, uniformly. So it could be this one, and that's your child 1, another random number, maybe that one, that's your child 2. You can make this a bit systematic like we did. We get to the half of it and we say one child will be created here, another child will be created here. Not only that, if you create this as the child for this parent, it will be the mirror image along that line will be the second child. So this is C1, that's C2. That makes it very, very systematic, and it satisfies some properties. Okay, but these are our addition, but their thing was just create any two random numbers. So alpha is a parameter. If you choose very small, then you are not going further away from the parents. If you are choosing alpha large, then you can go far away. Our description was different. We actually looked at binary codes, binary strings. If we code into real numbers and do single point crossover, what's the distribution of children we get? And we defined some non-dimensionalized parameter called beta. And over that, we found this kind of distribution is what we get from the simulating the binary crossover operator. So there is a bit of theory behind all this. But to tell you how you should do, instead of going into the details, is this. You create a random number between 0 and 1, then create these quantities, beta q, that depends on the random number and a parameter called eta. For all single objective, eta c, we call it for crossover, is around 2. 2 to 5 is what we used. And for multi-objective, we've gone up to 10 to 20. And there is a reason why you have to increase. Okay, so that's a parameter you set beforehand. You get this beta q, and then you take the parent value p1, p2, and with the beta q, you update and find c1 and c2. What happens is this. If this is your, no, probably sitting is better. If this is your p1 and this is your p2, all these I'm doing here, and the previous slide I showed you, you have a probability distribution that looks like one of these curves. Let's take the solid curve first. This is for eta equal to 2, which means these points which are close to the first parent and these points which are close to the second parent are very likely to be created as a child. The ones that are far away from either parent or even here has a very small probability to be created. This is what we observe if we have coded this in binary strings, both of them, and apply a lot of single point crossovers and look at the distribution. And it also makes sense because in real space, if this is your parent, this is likely to be an inherited child, something that is close than far away point, right? That's why the distribution reduces as you go away from the parents, so bimodal distribution. So this parameter, what does it do? If you have eta equal to 2, you have this. So if you say, what's the probability of creating one as a child from two parents, which is 2 and 5? You see, there is a good probability. But now if I choose eta equal to 5, dashed line is my probability, it's more picky. Now I have a much smaller probability, almost half the probability to be created 1 as a child. So eta is a way you can control how far your children can go. One way the children go is by the location of the two parents, the other is by the eta. So look at these two. When your P1, P2 are at 2 and 5, you have a fairly broad probability distribution. But when your parents are now close by, 2 and 2.5, they are very close by, you see the same eta equal to 2 distribution, they look like this. Okay, so this happens initially when you have initial random population all over the space, your parents are far away from each other, you have this kind of a thing. That means you can go far away, you can create a child right here from 2 and 5. But when you are, this is towards the end, right? You are converging, your population is now, you saw those simulations, right? You are converging, now your parents are close to each other, now you cannot go far away. So initially it helps you search in the entire space, later on it helps you focus. And all these are adaptive. I have not put any other parameter. I just set the eta c to be 2 right in the beginning. And it, depending on the population diversity, the children, their relative position from the parents get decided. These are sometimes known as self-adaptive properties. And on top of this, you can control with the eta. So eta is more like a global control, and then these distribution that we came up with does the local control. Any question? All right. This does phenomenally well in various problems. I mean, compared to binary coded, compared to BLX, this does very well. But just to tell you that, not going into the details here, but it does much better than BLX as well as binary coded GM. You can extend this for bounded variables. So let's say my lower bound is here and my upper bound of the variable is here, okay? But I have two parents, one is close to a lower bound, the other is somewhere there. So if I don't respect the bound, my probability distribution goes to minus infinity and plus infinity with long tail. So I could create a child here which is outside the bound. So what we do simply, we calculate this area, which is probability to fall outside the range, and distribute it here. You see there are two lines, so this probability has gone up a little bit. Same thing here, we calculate this distribution and distribute it here. So now it's not symmetric, but at least has the same feature. So if your parent is almost at the boundary, you have almost 50% chance of creating it right there, and other 50% going inside. Okay, so there is a reason why your parents is at the lower bound. Like you remember the solar problem, one of the variables hitting the upper bound. So there is a reason that, because you want to have more and more solar area to have more and more profit. So this kind of algorithm encourages more points to be created there. Okay, so everything is well thought of when you do these things without any parameter. If you have discreteness in your search space, like the casting problem, they come in integers or at step of 0.5 in this case. If you have this parent and that is another parent, you assume that there is no discreteness, and then you discretize the, so if you have this point, you just discretize it, get to the nearest one. So all you have is the silo wood becomes this distribution, but then it's a discrete probability distribution. So this also works, okay? I think we should stop, right? Yeah, just finish this one. Now the mutation, what you do, one simple idea would be, if you're here and you go to lower bound to upper bound, you can create any point at random, which I don't recommend because this is like random search. You don't want to do that. This is a good one. You have a point here, you do a normal distribution. Unfortunately, you need to set a sigma. So there is a literature called evolution strategy. There they talk about how to set the sigma. So we sometimes take ideas from there and set our sigma. We've come up with this polynomial mutation, which is again become default, where it's sort of like the SBX, but here there's a parameter called eta m. Usually for single or multiple objectives, the same thing. We usually go from 20 to 50. Sometimes we use 100. The effect of that is 1 over eta m is in the level you have the change. So if you do 50, 1 over 50 is how much? Is about 0.02, right? So you will have a change of mutation is going to happen at that range. If you want more, then you have to reduce it to maybe 20 or 10. If you want less, then you have to make it higher. So that's the effect that you get. Okay, I think I'm going to skip the vector-wise because they are not very popularly used, but after the break, I'm going to come and talk about 3 real parameter evolutionary methods: differential evolution, particle swarm optimization, and evolution strategy. So this is another way of doing evolutionary computing or evolutionary algorithm. Again, there is a population. So with these populations, you want to create a child, right? So what you do is you pick 3 solutions: x1, x2, x3. Now these are vector-wise operations, not variable-wise. So you take the difference between x2 and x3, so x2 minus x3, in vector operations you do. You multiply it by lambda. Lambda is usually less than 1, so let's say 0.7, 0.8. So you shrink this vector, let's say you make it this much, and then add this to x1, okay? So adding to x1, this one, and you get the new point called v. Okay, this is also a vector on the n-dimensional space. And then you pick another solution called xk. Usually they use the best of the population. So the population member having the smallest f. That one you pick and apply these crossover operator, as they call it. What is that? With probability p, you pick a value, a component from v. With probability 1 minus p, you pick a value from this. Now p is another parameter. So usually you can keep it close to 1 or keep it close to 0. If you keep close to 1, then more and more you are taking from here. So your solution is most likely be here. If you do very close to 0, then you are mostly here. Okay? So that means you don't want to go too far away from best. In this case, you are more explorative. Okay? You are going to go away from the best. So this is, and you create one child. So one child is created using this operation, and that goes into the population. Before they do that, actually, they compare y, the solution that is maybe y is created here, that y with xk, this one, you compare. If this is better than the best, then only you accept it. Otherwise, you don't accept it. But there are several versions. Again, you can have a probability here. With probability 0.75, you can accept this one, or 0.25, you don't accept this one, something like that you could do as well. All these algorithms, you see, there is a difference operator. Even in SBX, we have the difference. BLX, we have the difference. I believe that difference in the parents makes this whole process self-adaptive. It just goes with the population diversity. So this is another way. There are several versions of this. This is pretty stable, and lots of people use this method because of the structure that they have. Okay. Again, there are several versions. You can introduce gradient if you have with this method as well. Next, I'm going to talk briefly about the particle swarm. So here it kind of mimics the birds that fly together, the fish that kind of swims together, right? That kind of idea proposed by Kennedy and Eberhard. So what happens is all these, let me see if I have a picture here. Yeah. So you see these birds, they fly, these flies or birds that fly together. So let's say I have a population of birds or population of individuals in my X space. So this could be my X1, X2 space, and I've got my current population. Every individual, let's say this individual here, I will independently decide what would be the next iteration's location. So let's say this is my current population here. And here is my ith individual, and I'm trying to decide where will it go next. Similarly, I'm going to do every one of them and decide where every point is going to go next. So these two gentlemen thought about how these particles decide. There are 3 components to this. One is how they have come to this place. So this one, maybe the next previous iteration, this point was here. This was the in population, the blue color. So it was here. So we take a vector from that position to this new position, okay? And that is one component, okay? Sorry. The second component is a difference between its best location so far. So let's say at this generation, this particle was the best position. That means I have a function value here, I have a function value here, I have a function value here, and this was the best function value. So that's its best location starting to now. So now you do a vector, you want to go back to that. So for the birds or the birds, it is thinking like every bird or every individual here, let's say, had maximum amount of flies that it could eat at certain position before. It remembers it, and it always tries to goes back to that one. Okay, so that's kind of a thought. It's personal best. So that is given here by that vector. Now that vector is reduced by a factor. It's a random number multiplied by a c. C is between 0 to 2. Usually they use square root of 2. Okay, so that's the factor. Usually it turns out it could be little more than 1 or less than 1, because this you multiplied by a random number which is between 0 and 1. So you get that. And the third component is more like a social part, which is, this is the part which is poorly understood. If you consider all particles starting from the initial one to current point, every particle had a location. Somehow the best point among all of these is remembered. Let's say that location was this. This was not this particle's best location. This particle's best location was that. But considering all the particles, cumulative best position was, let's say, that one. As if out of all of these points, this one has the smallest function value so far. It's not still the minima, but it was the best one. So everyone, somehow this is communicated to everyone, and you always want to go in that direction. So there is another part here, if you see, again multiplied by another constant. Usually it's kept same as C1, and another random number. That's important thing, multiplied by the location of the global best minus the current position. So these three things are vectorically added, and you get a new position. So this one is going to move now there. So this one is separately I did there so that you can see these three components. But this is the vector becomes the result of that, and that's added. So as if like this particle was coming this way, let's see, this way, and then it turned. So it's the effect of all these three things as allowing it to turn, trying to go back to its original place, its own best, its global social best, and the way it came. So the inertia has to be there too. So this is done for every particle. Okay, the fitness function information coming from defining global and local, the current best and the global best. So they believe, and they use this, and they show similar simulations of birds that happens. So that's their kind of validation that this formula works like the way the birds travel. So this is what is done, and then you keep running this method and you eventually get near the optimum. Again, there are a lot of variations to this. You may go out of bound. When you have variable bounds, these are very difficult to satisfy because they are free from search. You can go anywhere with these vectors. But if you have restricted, if you hit the boundary, you have to get back. So how do you handle boundary becomes an important thing. So there are some caveats here, but they also do the social best that I mentioned. Instead of entire population, sometimes they have a structure here. These are individual swarms, individual swarm of particles. The whole population is divided, and then you say this neighbor is only that, this neighbor is only that, or this neighbor could be only the two nearby, or it could be all connected. So you define this architecture and then keep running this simulation, and they show that you can solve different kinds of problem differently if you use these different structures. So it's a well established literature on this. And the PSO, they have people who are only working in PSO, they have their own conferences and all that. Okay. Last one along this is evolution strategy, was again by these two persons from Germany. Almost at the same time as GA was developed in US, evolution strategy was developed in Germany. Okay. They started with two versions of it. One is 1+1, the other is 1,1. Yes, I'm going to describe to you what are these. And they did a lot of experimental optimization. Okay, so let me explain first 1+1. You start with one parent solution, one guess solution, right? And then you mutate it around it using a Gaussian mutation, like I showed you. Create a child, evaluate the child, compare with the parent. If child is better, call the child a parent, and then keep doing this. If child is not better, throw it and create another child. So like that, it's a very simple algorithm. So with that, they could do lots of these experimental things. You see there is a pipe that ends here. There is a pipe that ends there, and they are 90-degree apart. He's trying to design this transition. So he starts with a perfect quarter circle, okay, like what we use, but these are flexible hose, and they had 1, 2, 3, 4, 5, 6 location you can pull or push. So change the shape of these. And they are not doing any model to find what will be the pressure loss or something. So you send some fluid this way, the fluid goes out, and they measure what was the pressure here, what is the pressure there. Now it will be little less because of this curvature that it took, right, with the friction and everything inside. So they're saying, okay, I am going to take the difference in the pressure between the two, and I'm going to minimize. So I want to keep as much pressure it's coming. What shape is going to maintain the pressure as much as possible? So it turns out that these are your variables, 6 places you can do plus or minus, and they did this kind of experimental setup. Later on, they put it with a computer where these things will automatically push and pull, dictated by an evolution strategy solution. And this is the starting point, and they come up with this as the result. Now that they see this, they also see this on 180-degree turn. You see it goes a little further and comes down. Now these are unusual shapes, right? So the first thing that comes to their mind, why are they not symmetric? Why is it having this property that you have to overshoot and then come with a parallel thing? Same thing you see there and here. Once you observe that this thing happens, you can now go to your pen and paper and computer and try to explain. And they have very nice explanation. This is considering friction inside and everything. So what you see is what you get. There is no assumption, right? Because you have actually done the experiment to see it. So this is called Bionic Lab, they used to call. I think Rechenberg is no more active. I don't think anybody is continuing there. But they did lots of such thing. They asked me to sip 3 or 4 times a little bit of coffee, and the guy gave me a slip with the recipe that how much coffee I should put on how much milk and how much sugar I should add so that I like it the most. Okay, so the fitness function is coming from where? 3 or 4 times that I sipped, and I compared with the previous one I sipped, and they ran an algorithm and gave me the recipe. So that kind of innovative evolution strategy methods they were doing. Okay, later on they kind of expanded it. They have mu parents. From them they create lambda offsprings, and then keep the best mu out of it, and that becomes their next iteration parent. And this goes here, and then you go into the loop. This is mu comma lambda. And then they have mu plus lambda, where you actually have mu parents, you create lambda offspring, you combine both, that's why there is plus. And then from the combined population, you keep mu. Each has their pluses and minuses, but these are the 2 versions they have. Later on, they have put also some recombination operators, which are very simple recombinations. It's known for their 1/5 success rule. The mutation sigma that I told you, they have a very sophisticated way of updating. They look at that with a particular mutation strength, which is sigma. They see how often you have created a successful offspring, means better than parent offspring. If 20% of the time or more you have created a successful offspring, then you increase the sigma. Otherwise, you decrease. So that was found by doing some experimental validation of this idea. It's famously known as 1/5 success rule. We try to do this in our evolutionary methods as well. Okay, I'm going to leave the recombinations because this is very simple recombinations that they do. They do a lot of sophisticated stuff like trying to find the correlation. So if you have population members line up like this in a problem, they try to find the correlation coefficients because those are useful to do. Then when you create children, you can orient them also. This is very famous algorithm called CMAS. You can find the code if you type in CMAS, again from Germany, Nicholas Hansen and Ostermeyer. It's a very popular code. They do a lot of sophistication. So this is called covariant matrix adaptation. So they are basically adapting the covariance of the population distribution. It's a little expensive, it's a little slow, but every few iterations they collect all the points, all the good points, and they look at their distribution of the good points in the search space, and they find the correlation coefficients, and that gets adapted every now and then, and that correlation is used to create new children. So it's not like SBX. It's not like the evolution strategy one. It's basically understanding my current good population members, what correlations they have, what kind of covariances they have, and they kind of follow that to create new solutions. So obviously these are better, but there are order n cube operations you have to do to understand that covariance, and that's why it is a little slow. Okay, but I would recommend this if you're doing a real parameter optimization with not many optima. If you have many optima, these ideas get confused because you have an attractor here, you have an attractor there, you have few points like this. If you try to do a covariance where there are two attractors, you don't get a very good information. But if there is a single attractor, everything works nicely. Okay, use these ideas to have mixed coding. Like one of your code could be to represent a design, could be one saying, do I have a circular cross section or a square cross section? Just one bit is enough. 0 means circle, 1 means square. Next one could be the dimension, D, or the size A. If it's 1, the next one says A, maybe in millimeter or whatever. Next one could be length. This could be a real parameter. This could be integer. This is a Boolean variable. This one could be material. So if I have 8 materials, I can quote them. So this string says, this is made of aluminum. This has a square cross section with size 14 millimeter and maybe 23.457 inch. I can have different units or whatever. So some of them are real, some of them are integer, some of them are Boolean, some of them could be a string. All these can stay in one population member. So when I'm doing a population of this and doing crossover, there is nothing to cross between two bits, but I can cross these two integers. I showed you discrete version of SBX, I could do here. Between two real numbers, I could do SBX. Between two binary strings, I could do a single point or 2-point crossover. Right? I'm never crossing this with that, right? I'm crossing between two parents which have similar structure. So it all works out. And we suggested this, we called in this ASME journal, we called Genius, Gene Adaptive Search. Okay? So you could do all of this. One of our RGA code can handle this kind of stuff. Okay, so I think I introduced you to evolutionary algorithm and showed you some examples and a little bit of idea of how it works and extended it for real parameters. So now that I have ways to handle discrete, integer or Boolean and real, you can put them all together, right? So you see how flexible that is.